Hi everyone, welcome back to Chem Story. Today we're diving into a really useful transformation, the oxidative cleavage of alkenes. Basically, we're going to take double bonds and slice them in half to make carbonyl compounds. There are three main reactions we'll look at: ozonolysis, cleavage with potassium permanganate, and cleavage of 1,2-diols. Each of these gives different products, like aldehydes, ketones, or even carboxylic acids, depending on how the reaction is done. Let's start with ozonolysis and break down how this reaction works. Ozonolysis is a reaction where an alkene reacts with ozone, and that breaks the double bond right down the middle. The result? Two carbonyl compounds, usually aldehydes or ketones. So here's how it works. In the first step, the alkene reacts with ozone and forms an unstable intermediate. Then, in the second step, we add a mild reducing agent, something like dimethyl sulfide or zinc in water. That's the step that actually breaks apart the intermediate and gives us the final products. So, to keep it simple, ozonolysis takes a CC double bond and turns it into two carbon-oxygen double bonds. It's clean, efficient, and a really useful transformation. Now let's take a look at the first part of the mechanism, how the ozonide forms. This all happens at low temperature, usually around -78 degrees Celsius. At that point, the alkene reacts with ozone and forms a temporary intermediate called a malosonide. But malosonides are really unstable, so almost right away, they fall apart and rearrange into a more stable structure, the ozonide. That ozonide is what we're going to break open next, when we add the reducing agent. We'll talk about that soon, but for now, here's the main takeaway. Alkene reacts with ozone, forms an ozonide, and that's what sets things up for the final cleavage. Let's take a closer look at how the ozonide actually forms and what's going on with the electrons behind the scenes. When an alkene first reacts with ozone, the two come together to make a cyclic intermediate called a malosonide. You can think of it as the first link between the double bond and ozone. But this malosonide doesn't stick around for long. It's really unstable. It quickly falls apart into two fragments, and each one carries an oxygen. Those two fragments then recombine to form a more stable structure, the ozonide. So overall, the process goes like this. First, a 2+3 cycloaddition to make the malosonide, then a fragmentation into open chain pieces, and finally, ring closure to form the ozonide. Now let's move on to step 2, the workup of the ozonide. This is where we actually decide what the final products will be, and it all comes down to which reagent we use. If we go with a mild reducing agent like zinc, dimethyl sulfide, or triphenylphosphine, we do what's called a reductive workup. That usually gives us aldehydes or ketones, depending on how the original alkene was structured. But if we use something stronger, like sodium borohydride, it takes the carbonyls one step further, and we end up with alcohols instead. On the other hand, if we go the opposite direction and use an oxidizing agent, like hydrogen peroxide, any aldehydes that form will get pushed further into carboxylic acids. So here's the key takeaway. Ozonolysis breaks the double bond, but your final product depends on how you work up that ozonide. Let's quickly sum up what kind of products we get based on how we work up the ozonide. If we use something like DMS or zinc in water, we get clean carbonyl compounds. That means ketones and aldehydes. This is the most common and straightforward setup. If we go with sodium borohydride, we take it one step further, and those carbonyls get reduced to alcohols instead. Now, if we use hydrogen peroxide, which is an oxidizing agent, any aldehydes that form don't stay as aldehydes. They get oxidized into carboxylic acids. That's especially important if your alkene had a hydrogen directly attached to one side of the double bond, because that's what gives you the aldehyde in the first place, and that's the one that gets oxidized. So the bottom line is, your choice of reagent really matters. It can completely change what you end up with. Now let's move on to another method, oxidative cleavage using potassium permanganate. This one's a bit more intense than ozonolysis. We use warm, concentrated KMnO₄, and under these conditions, the reaction goes all the way. So if any aldehydes happen to form in the process, they won't stick around. They get fully oxidized into carboxylic acids before you even get a chance to isolate them. So with strong KMnO₄ like this, you're always going to end up with either a ketone or a carboxylic acid, depending on what kind of alkene you started with. Let's walk through what actually happens in this KMnO₄ reaction. We start with an alkene, just like before. The first thing that forms is a glycol. That's a 1,2 diol, with hydroxyl groups on both sides of where the double bond used to be. Then KMnO₄ comes in and cleaves the carbon-carbon bond between those two OH groups. The result? 2 carbonyl compounds, just like we saw with ozonolysis. But here's the big difference. If one of those products would have been an aldehyde, KMnO₄ won't let it stay that way. It pushes it further and turns it into a carboxylic acid. So depending on what groups were originally on your alkene, you'll end up with either a ketone or an acid, no aldehydes left behind. This is a strong, irreversible type of oxidative cleavage. There's one more method we should cover, and that's the oxidative cleavage of 1,2 diols. These are molecules that already have 2 hydroxyl groups on neighboring carbons, just like the ones we saw earlier from the KMnO₄ reaction. Now, if you treat those 1,2 diols with reagents like periodic acid, sodium periodate, or even lead tetraacetate, the bond between the 2 OH-bearing carbons gets cleaved. And just like before, you end up with 2 carbonyl compounds, either aldehydes or ketones, depending on what was originally there. That makes this a great follow-up, especially when you already have a diol in hand. You can take it one step further and cut it cleanly into useful carbonyl fragments. Here's a great example that brings everything together. We're starting with an alkene, and we want to break it down into 2 carbonyl compounds. If we go with ozonolysis, we treat the alkene with ozone first, then follow it up with zinc. That gives us a ketone and an aldehyde. But there's another way to get there too. We can take the same alkene, do a syn dihydroxylation using osmium tetroxide, and then use sodium periodate to cleave the resulting diol. Mechanistically, the periodate forms a cyclic intermediate called a periodinate ester, and that breaks apart to give us the exact same pair of carbonyl compounds. So whether you go through ozonolysis or diol cleavage, you can end up with the same products. It just depends on which route works better for your conditions. Alright, that brings us to the end of our deep dive into oxidative cleavage of alkenes. We looked at ozonolysis, potassium permanganate, and 1,2 diol cleavage, and saw how each one breaks CC double bonds to give carbonyl products. These reactions are super useful, not just for figuring out structures, but also for building new molecules in organic synthesis. Thanks so much for joining me today, and as always, I'll see you in the next Chem Story video.